Okay, so the first, last and only speaker today is Robert. Rob is going to tell us about primary fields in CFT4.
Okay, thanks. So I was listed as an organizer, but that's just really false advertising. The only organizer was Vishnu, so Vishnu, thank you for the job to talk. So the work I'll be discussing today was done with Pramod Rambambi, who has just completed his PhD, with Rand Overall, who completed his MSc and he's now doing a PhD with Koch at Victoria, and with Sanjay Ramgulam, long-time collaborator, and then on another paper together with Pramod and also Yaku, who most of you have met by now. Okay, so what is the idea? So recently, I guess there's been a resurgence of interest in CFTs, and one of the ideas that's floating around is that there's a list of CFT data, so that means a list of primary operators and OPE coefficients. Something like the conformal bootstrap is an approach to try to constrain this data, and one of the loftier goals of the bootstrap is that you would like to achieve even a complete classification of the set of possible CFTs. So one very pedestrian question you could ask is, for any of these CFTs, I've never seen a list of complete CFT data. So can you make such a list? What would it look like? How would you present it? And the simplest case where you could try to do that is with a free boson or fermion, and this was already not easy. And if you can't do it here, then you can't do it anywhere else. So for the free boson, free fermion, free vector model, free matrix model, we will be able to at least say what are the primaries, their dimensions, their spin, and what multiplicity you have for each primary. Another motivation could be that free CFT is useful as a starting point for interacting CFT. So, for example, to understand the Wilson-Fisher fixed point and anomalous dimensions of that fixed point, Richkoff and Tam have showed that you could use data from the free CFT to get hold of at least one with anomalous dimensions. Another motivation is that the free vector model already has relevance for holographic descriptions of higher spin theories, following the work of Polynomial and Representation. And finally, this is an application that we only learned of after we finished the work. If you look at low energy effective field theory, so you're writing down, say, even some corrections to the standard model, the higher dimension operators that you could write down, you'd like to know what's a complete set of them that you could write. And the reason why that's not completely trivial is that you've got integration by parts, so terms that look naively different might be exactly the same. And you also have field redefinitions. So how do you write down a basis that is not overcomplete? And it turns out that representations of free field theory allow you to solve that problem, and these authors really explain how that works. Okay. So what are we going to do?
You have in mind CFT in D bigger than 2 now.
D is equal to 4, in fact. So the methods you can use in other D, but we will only focus on D is equal to 4. Yeah. So the first thing we're going to do is consider counting primaries constructed using n fields. And so we'll start off just using a free boson. And building n fields, we'll try to make a list of what primaries you could get, and then we'll extend that to free vector, free matrix, and then finally a free fermion. So once we've figured out how to count these quantities, you'll see that we've actually learned something about their structure. Once you've managed to count them, you'll be able to construct them. Part of the construction that we'll do is we'll use a polynomial representation for the conformal group. We'll actually reduce the problem of constructing primaries to the problem of constructing translation invariant and harmonic polynomials. So I'll explain to you how that works. And then finally, I'll show you some explicit expressions for families of primaries that weren't known before. So things like the conserved currents and things like that, they were constructed long ago. So we'll construct some other families that weren't known.
So will you count these primaries or construct them? Or both?
Both. Yeah. So we'll start with counting and then construct.
Unless n is equal to 2, there are no short representations. Is this right?
Absolutely. Yeah. Well, with n is 1, of course, that's also short.
Yes. Yeah. For n larger than 2, there are no short representations.
Exactly. Yeah.
So you can just compute the character and then model it.
Exactly. Exactly. Okay. So the number scalar is in a representation which has got dimension 1, spin 0. The primary is 5 naught. Descendants are given by traceless symmetric polynomials and derivatives acting on 5 naught. The reason why they're automatically traceless is that there's a null state corresponding to the equation of motion. So the trace part of anything that you write down automatically vanishes. For products of n-scalar fields, because we're talking about bosons, we have to take the symmetric product of n copies of this representation. And then we want to decompose that into a unique sum of irreducible representations. Each of these irreps corresponds to a primary, so that decomposition, if you manage to carry it out, will give you the list of the primaries. So if you want to enumerate primaries constructed using n fields, it's a two-step process. Number one, can you compute that character? And secondly, decompose it into a sum of characters of irreps. So that's what we want to do. Okay, so
So what you're trying to solve is just map the Fock space representation to the conformal group.
absolutely.
That's all.
Organize the Fock space
Yeah.
for n free bosons, n is general, under the conformal group. Exactly. Okay, so if we take M inside any group in irrep R, a useful formula that we're going to make a lot of use of is 1 over the depth of 1 minus t times n, actually is a generating function for the character that we want. And the reason why we're taking the symmetric representation is we've got bosons, so we need to symmetrize. So we're going to apply this to the case that M is an element of SO4. The element we're going to pick is just S to the dilatation operator, X to the J3 left, Y to the J3 right. These three guys commute, and they uniquely label any state that we've got. So if you take a look at what states you would get inside this representation, just for V+, so we've got a single field, you've got your momentum operators acting on there. Each momentum operator adds 1 to the dimension, plus the field by itself. So this has got a dimension of Q plus 1, it is QPs. It's symmetric traceless, so we know that this is in the spin Q over 2 Q over 2 representation. So when we come to calculate this determinant, we need to take a product of a factor for each state. So we've got S to the Q plus 1 and XA. A goes from minus Q over 2 to Q over 2 for the right spin, and YB, Y goes from minus Q over 2 to Q over 2 for the left spin. So you could plug this into Mathematica, expand it out as a function of t, and pick up those characters. Good. So the next step is we want to take this character and rewrite it as some coefficients times characters of the irreps, and these coefficients would all be integers. These integers exactly count the number of primaries constructed from n free bosons with dimension delta and spin J1, J2. The relevant character for us, this is assuming no null states, looks like S to the delta, K, chi J1 of X, chi J2 of X. Chi are just SU2 characters, and then we have that denominator sitting there. Now the way to understand this formula, first of all, notice that the quantum numbers of the primary only appear in the numerator. The denominator is the same for any representation that you pick up. And remember that there are 4 components of momentum. The momentum operator has got dimension 1. It's in the 1/2, 1/2 representation. So J left could be plus or minus 1/2, J right could be plus or minus 1/2. This S square root xy, if you expanded that out, that would be generating all of the descendants from the component of momentum with left spin equal to right spin equal to plus 1/2. Similarly, this term would generate all of the descendants from the component of momentum with left spin equal to right spin equal to minus 1/2. So the denominator is just telling us all about the descendants, and there's no information there. So let's remove it. So instead of writing this as a sum of characters, let's produce a new function z that will just simply give us the sum of s to the delta and the 2 characters. And if you compare chi to this z, what do we want to do? We just need to multiply by those 4 factors over there.
Here you're assuming n is greater than 2.
Absolutely, we'll come back to n is 2. Yep. So assumption no null states. Then we can simplify it even further, because instead of having characters there, we might just like to have these 2 variables to this power, and there's a very simple trick to do that. So if, for example, take chi2 of x, if this is the spin 2 representation, jz would be able to vary over 2, 1, 0, minus 1, minus 2. Those are the different terms appearing over there, just x to the j. If you multiply by 1 minus 1 over x, you can see the 1 over x times the x squared cancels with the 1 times the x, so almost everything cancels. You're left with an x squared minus 1 over x cubed. So if you multiply by 1 minus 1 over x and 1 minus 1 over y, and you keep only positive powers of x and y, you will turn this expression zn, which has those characters, into this expression gn, which only has those two variables raised to some power. So that's basically the object that we want to calculate. Now for n is equal to 2, we have null states. So for n is equal to 2, you can get higher spin conserved currents. These guys saturate the unitarity bound. So you know that there's going to be a null state, and that null state just corresponds to the conservation law. So in fact, the operator that is null here has dimension 3 plus 2j, and it has j1 equal to j2 equal to j minus 1 half. You've lost one index. In the remaining indices, you're still symmetric traceless, and your dimension has increased by 1 because of the derivative. So to subtract these null states, what should you do? Well, there is the multiplet, and this would be the representation that you get by building on top of that null state. So you just want to subtract it out. At the end of the day, if you go through this process, what happens is, there's the denominator that we used to have, but we've got this extra factor sitting at the top. And this extra factor here just removes one of the derivatives. So you don't produce descendants with the derivative that gives you the null state. So to do the counting in the presence of null states, there should only have been 3 factors in the bottom. In fact, our Zn was defined with all 4 factors over there, so we should not have removed this factor here, which doesn't appear in the denominator. So for counting null states, you would do the following. At n is equal to 2, there's one operator that's not short. That's delta is equal to 2, and the spin is equal to 0. So subtract that out of Z2. Once you've subtracted it out, put that guy back in that you shouldn't have tried to remove, carry on with the same procedure, and in this particular case, that's the result you get, and that's just equivalent to the Flatters-Ronstadt theorem. So you multiply 2 scalar fields, you'll get the delta is equal to 2 primary plus all higher spin currents. Now, the expression that I showed you is not very useful in the form that it sits, so what you can rather try to do is focus on a subset of states. So we started to focus on what we call, well, the leading twist primaries. Yes,
Is there a simple way of saying why there are no null states for n greater than 2?
Yes, there is. So to saturate the unitarity bound, I'll refer you to Shiraz's paper. Was that the first paper you wrote, Shiraz?
Yeah.
Okay. So it's got a very nice explanation of the unitarity bounds there. So what happens is the dimension has to be small enough to saturate the bound. As soon as you've got 3 fields, you already have too much dimension to saturate the bound.
Oh, the difference has to be lower than, the difference is 2, right? If you have 3 fields, then you can't.
Exactly.
Exactly. Fine.
Okay. So, okay. Strip. Okay. So now let's pick the primaries that have the highest possible spin for the given dimension. And if you do that, and for each of these primaries, of course, it's a spin multiplet of q plus 1 squared operators, but let's just choose the single state with highest spin. So what we do is that these powers for the x and the y, we no longer take a product going from minus q over 2 to q over 2, we just select a single state. And this will now count for us the primaries of leading twist. The other difference is, because we're just keeping one of the states, the one with highest spin, we only keep one component of momentum. And that's the one with biggest J left and biggest J right. So this factor over here gets replaced just by a single factor. And lastly, we didn't keep the whole character because we only kept one state from each spin multiplet. So we're not going to get the character appearing, we're already going to get the x's and the y's to whatever power. So we don't need to multiply by that factor and keep only positive powers. So at the end of the day, for the leading twist primaries, this is the formula that you would get, and it's much easier to evaluate. And in fact, you can evaluate that in a closed form, and that's the answer that you get. Here, I've dropped x and y because, well, as soon as you know the dimension, you know the 2 spins, so I don't need to track those anymore. This is a very simple counting function. The reason why it's interesting is it suggests that this is the counting that you would get if you were studying a freely generated ring with n minus 1 generators. And a little bit later, I'll show you exactly what this ring is, and it gives you a very nice construction of these higher twist primaries for any n.
So how do I read this formula, please?
Oh, you mean this one over here?
Yes, please.
Okay, so s to the n sitting here, this is the dimension coming from the n fields.
Yes.
Each of these factors sitting down here is some combination of derivatives that you could be acting. This one will be 2 derivatives just by the dimension, this 3, and so on. And the fact that there's no extra bits sitting over here means that when you multiply this thing out, each of these can act independently, there's no relations between them. So there's really n minus 1 different differential operators that you could be applying to these fields to generate all of the primaries.
And there's no relations because they're all derivatives in the same direction, so they can't make del squares.
Absolutely, yep. Yeah.
Okay, and this s couples to basically the dimension. It's this s to the power n.
Exactly.
Thank you.
Now, you could also look at what we call extremal primaries. This might be a bad name, so it's not the same as extremal anywhere else. So we fix the left spin to be as high as you
Sorry,
like.
one more question. Please, why can't you have one? It's not possible to have one derivative. You saw s squared.
You mean, that's right. So we're going to see.
It's
not.
not.
Yeah, I'll show you why. Yeah. In fact, yeah, I'll show you why. Okay. So for the extremal primaries, so we set delta, we set J3 left to its highest value, but we still allow J3 right to vary over values. So the power of x is fixed, but y instead, in fact, still varies over the range that you wanted, and this will generate for you a different set of objects that will be counting this class of primaries. In this situation, in fact, we fixed one of the spins to be maximal, so we can have a square root xy or a square root of x over y. No 1 over square root x's. And that means that the y's will in fact be summing still complete multiplets of states, so we'll need to turn the character for y back into just a power. So this is the counting function that we get at the bottom here. And if you look at that counting function, here are just a few examples. So calculating in general was a little more difficult, but these are 2 results that we got with Mathematica. Now here is an example where you can see this. So to read this formula, s cubed, that's for the 3 fields. And then you'll say there's 1, 2, 3, 4 different combinations of derivatives that you could act to get these primaries. The reason why you got this 1 minus s to the 10 x to the 5 y cubed is because, in fact, so we checked this in detail, if you square this generator over here, it is not independent from taking that generator multiplied by that generator squared. This generator squared is an s to the 10 x to the 5 y cubed. That guy times this squared is also s to the 10 x to the 5 y cubed. And that minus s to the 10 x to the 5 y cubed is just subtracting off the overcounting that you would have done if you didn't take into account that not all of these are independent.
I'm sorry, you said this. What is an extremal primary, please? What is extremal?
Extremal means right spin is maximal. So left spin can still vary over whatever you like, but we fixed the right spin to be maximal. For G4, it's a lot more complicated. In this case too, we check that the generator satisfies certain relations, and this correctly encodes those relations. So it still suggests that there's a ring sitting here, but now that the ring is not freely generated. So can you construct that ring? So that was the next thing that we looked at. So what's the algebraic problem that we're trying to solve? That's the SO24 algebra. What's a primary operator? You want it to be annihilated by special conformal transformations, and because we're dealing with free field, you'd like to impose this on each field. Okay, just the equation of motion. Okay. There's a nice polynomial representation that you can use, and it represents K, P, the rotation operator, and Lorentz transformation that you will put many Euclidean space in this form. So what have you done? I think that you're used to P being the derivative and K being more complicated. All that we did was do inversion, the previous differential realization, and then inversion again. The dimension of the scalar field sits over there and over there. So you can generalize this. Let's say we're dealing with n fields. Then we get a representation by saying let's use n coordinates x mu I with I going from 1 to n. And we have the normal Koch product acting, so k mu would look like that and p mu would look like that. Now, what is the condition that a polynomial that corresponds to a primary operator must satisfy? If you calculate p mu, which should be set to 0, this is just x to the 4 d mu d mu. So it's telling you your polynomials must be harmonic. The condition that k mu annihilates your wave function is just the statement that this is invariant under overall translations in all of these coordinates. So I'm going to call this translation invariant for you to be a primary. I'm going to call this harmonic. This means harmonic. And over here, we're going to say that it must be SN symmetric. When you study the leading twist and extremal primaries, these correspond to holomorphic polynomials. If you've got a holomorphic polynomial, you satisfy the harmonic condition automatically. You then make a translation invariant, which is an easy problem to solve. I'll show you how to solve that now. You just pick a nice set of coordinates and build the polynomials out of those coordinates. So at the end of the day, the problem becomes something in symmetric group theory. You just look for something that is invariant under the symmetric group. And then you can pose this as a nice algebraic problem where you can do the counting again, and you can actually write at the end of the day the polynomials that you get as some sort of a symmetric group projector, and you need a rule to translate the polynomials back into operators, but you can give such a rule and in that way construct the operators. So that's going to be the logic.
Sorry, I'm a bit confused.
Yep.
Super stupid question.
Yeah.
Why are these derivatives acting on each independent coordinate? I thought you're making local fields, right?
So, yep, we're making local fields. That's true.
So what are these different coordinates?
Okay, so what we're doing is, we're imagining we're starting off and these fields are all distinguishable. So you've got 5x1, 5x2, 5x3, and so on.
Yes.
So we imagine this acting on n distinguishable fields.
Yes.
Then we want to turn these back into bosons located at the same point. And that we do with the symmetric group condition over here. So we're starting off, we're making the space bigger. We want to consider, say, 4 fields, 5x, 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 5x. We're making the field bigger, 5x1, 5x2, 5x3, 5x4. They were symmetric, we're projecting to stuff that's completely symmetric. That will then give you the bosonic thing, which is in the
Sorry, but completely symmetric does not mean that they are at the same point. If you start with fields at different points and you symmetrize, they are not at the same point.
They're not at the same point, but this thing is completely symmetric. Once you've gotten that guy that's completely symmetric and you put all of the coordinates equal to each other, that will give you the primary. So
that's true, but okay.
So the proof for that will come from counting.
To understand correctly, these x's are not the usual x's, right? You've inverted.
Yes,
These
okay.
x's
Yeah,
we've
that's
inverted. Yes, they're not the usual space-time positions, that's true.
Okay, that's a detail.
Well, that doesn't affect this visualization.
No.
Just, you can undo it. At every stage you can undo it and work with it.
Okay, so let me show you what the x's correspond to. So we're going to want to translate polynomials acting on our field into x's, because we're changing from momenta acting on the operators to some set of polynomials and want to solve the polynomial problem. So if you have some symmetric traceless combination of b's acting on 5 naught, what this translates into our representation of the symmetric group of Extremal is this factor sitting over here. This object over here, which is a projection operator onto symmetric traceless representations, and there's the x sitting over here. So, and it goes both ways. So if you give me some polynomial, I can translate that into some momenta.
Well, I guess that's why, because the derivatives can act on all the operators. That's why you have different x's.
Yeah.
That's why it makes sense. Oh, okay.
So it's keeping track of which field you differentiate.
I see. I understand. Okay. Thanks.
So we'll introduce these complex coordinates. We can choose our conventions for SO4 so that those complex coordinates of those SO4 quantum numbers. Then the thing that we call the leading twist primaries will be polynomials built just out of Z. And the things that we call extremal primaries will be polynomials built out of Z and W. And you can see at this stage, at this stage, if we're going to restrict ourselves just to holomorphic polynomials, we don't even have to worry about the condition these polynomials are harmonic. They're automatically harmonic. So what does that buy for us? We solve one of the constraints.
So, and the condition that it's not a descendant, that it's not a total derivative or something, where is that?
That means it's annihilated by K. And to be annihilated by K, you must be invariant in translations of all of the coordinates. So this is going to be particularly useful later if you've got pz to the k acting on the field. This is some factor times e to the k. pz to the k, pw to the l, so some holomorphic combination of the derivatives acting on the field is z to the k, w to the l plus some factor. So,
Can you go back to that?
sure.
Here you pick one complex structure to...
Exactly. Yeah. Okay. So we've got these x mu i's. I goes from 1 to n. We've got an action of the symmetric group on these i's. It'll just swap these x mu i's around. So this is what's called the natural representation of Sn. It's reducible. It's a direct sum of V naught, so this is a one-dimensional representation, which is a Young diagram with a single row of n boxes, direct sum with the hook, and the hook is a representation with n minus 1 boxes in the first row, 1 box in the second row. And this guy over here, which is just the center of mass coordinate, that spans the symmetric representation, and this coordinate over here for a inside 1 up to n minus 1 spans the hook. So if we now start to consider holomorphic polynomials in those hook variables, the only so holomorphic means they're definitely harmonic. If they're in the hook variables, it means they're translation invariant. So the only condition that we have left is to impose Sn invariance. And that's a nice algebraic problem that we know how to impose. So there's a large simple class of primaries that have that form. So that's what we're going to focus on. So now let's try to construct the leading twist primaries. So if you take ZA and you study some polynomial of degree k, so A can go from 1 to n minus 1. Degree k means we're taking the hook to the kth power. And so first of all, you've got an action of Sn, because this is the hook. So you've got an action of Sn on each of those vector spaces. But then you've got an action of Sk, which swaps these different vector spaces around. And you can ask yourself, so for a given, if you take this to the power of k, you'll get representation lambda 1 of Sn, representation lambda 2 of Sk. How many times will it appear? Well, it's given by the dimension of this vector space over here. And what you need to do is you need to find the centralizer algebra of these two guys. In this case, it's something that's well studied in the math literature. It's called the quasi-partition algebra. And the dimension of that vector space will actually be related to the dimension of some irreducible representation of the quasi-partition algebra. So these dimensions are telling us about the primaries that we want to construct. In our case, we want a symmetric, the symmetric product of n copies of the field. So we're going to choose lambda 1 to be a single row with n boxes. And all of the derivatives commute. So lambda 2 must also be chosen to be a single row with k boxes now. The generating function for the dimensions of these spaces was calculated in old Koch-Sanchez. And the answer is given by this expression over here. And what's nice is all of these quantities, Ci are the length of the ith column in lambda 1, B runs over the boxes in lambda 1, HB is the hook length of box B. So this is all nicely determined completely in terms of the Young diagram. So very, very explicit formula for those dimensions. So if we now form this function, sum of k, q to k, k, it's that answer over there. And what we find is Gn max is just given by s to the n, which we need to put in by hand. That's the dimension for the n fields. And times by this counting function over here. SH just stands for simple hook. What that means is, if we work inside the space of polynomials of degree k, so in general we will have k different indices, a1 up to ak, we just take the projector onto the symmetric, and counting how many states we get matches the number of primaries, so this gives you a way to actually construct the primaries. You just act with this projector on these polynomials. So let's look at n is equal to 3, for example. Here would be the two hook variables. It's straightforward to write down 2 of the elements of the symmetric group, and everything is generated by these. To construct gamma k, the matrix that would act on a degree k polynomial, you simply take tensor products of these two guys, and the primary that you're after would be given by taking this projector and that projector and acting on this polynomial. And you need to look at elements of this, extract them, but then the claim is the polynomial that you get over here, translate it back again, turn the z's back into derivatives, and that should then be the primary of the CFT. So let me give you a very simple example. For n is 2, that's the translation invariant variable, that's the only book variable that you've got. If you raise this to the power of 2k, that's the only time this has to be even for you to get an invariant of the symmetric group. But this we would claim is the full set of polynomials corresponding to primary operators. If you translate this back into a set of derivatives, so you need to take into account those factorials and signs and things that they were appearing previously, you reproduce the highest concurrence of Craigie, Joburg, and Todorov. And you can do it also for, okay, so let me show you one other thing. So recall that this looked like you had a ring structure. What is that ring structure? So for n is equal to 2, you've got a single variable, which is z1 minus z2 squared. Now, the reason why you couldn't get something with just a single derivative is that z1 minus z2 would be harmonic, it would be translation invariant, but it would be antisymmetric under swapping z1 and z2. So it just wouldn't satisfy those three conditions. For n is 3, you've actually got that object, and now you get a second hook variable that you can produce, and you can make that symmetric. So for n is 3, these are the two guys that would generate the entire polynomial ring. For n is 4, that would be the new generator, but it becomes a very systematic thing. So at any n, you can write down the complete set of generators, you can write down the set of polynomials, and you can translate these back into primaries. Okay. Now let's look at constructing extremal primaries. So this is a little bit more interesting. So we're going to look at something that's degree k in z and degree l in w.
So it follows from what you said, if you go back and say,
Sure.
Can you intuitively explain why this ends at 1 minus x to the power n? From the point of view of just sprinkling derivatives.
Yeah.
Ask the question again, please.
Why does it end at 1 minus x to the power n?
So you're asking, is there a nice way to see why there are, yeah. So let's see.
I know it follows from your construction, but
Yeah, I know. So let's see. Is there a simple way to see that?
it's not a very well posed question.
No, I like the question, yeah, but I don't know the answer. Okay. So if we take a polynomial degree k in z, degree l in w, the same thing, take the product of these two, and what will this polynomial transform it? It'll transform the tensor product of that space with the tensor product of this space. We're again going to ask to get an Sn invariant. So we want to combine this representation of Sn with that representation of Sn. To get an invariant, all that you need is lambda 1 to be equal to lambda 3, and the invariant always appears once in the tensor product. So we're going to set lambda 1 equal to lambda 3, and then sum over lambda. Lambda 2 and lambda 4 still have to be the trivial representation because the derivatives still all commute. So this would be a single row with k boxes, single row with l boxes, and then we've got these two vector spaces whose dimension we know how to write down. So again, that's the generated function for the dimension of those two vector spaces. So you can now write down the counting function, just based on solving the symmetric group problem, as that answer over there. And again, if you work out what this function is, it agrees completely with the character answer that you got previously. So we know we're counting the same things. So you could again take a projector, apply it to some set of w's and z's, and get primaries. So here is an example. So here we wrote down a few families of primaries. Here's just one of them. So this is n is equal to 3. We're using w and z bar. So this particular polynomial is harmonic, translation invariant, and symmetric. And if you translate this into an operator, that's what the operator would look like. There are the three fields sitting there. There are the sums. These factors come from the translation. And you can go ahead and check if this really is primary, and it is a primary. But it's quite easy to generate whatever families you like. So far we've used this crutch of making things holomorphic, which simplified the equation of motion constraints. What happens if you want to consider the whole problem and the full set of primaries? So I'm not going to talk about that. Sanjay and I discussed that in our most recent paper. In this situation, you still get a ring, but the harmonic condition, you have to account for that. So what we ended up doing, wrote the harmonic condition, so there's n of them, it must be harmonic in each of the coordinates. And we rewrote that using the hook variables. We were able to show that there's a gainer in structure. So this might surprise you, because if you've got a harmonic polynomial, you multiply by another harmonic polynomial, the product in general is not harmonic. But we had to introduce a star product to make things work, and you were able to prove that the star product is associative. And in that situation, you were able to give a construction algorithm. It was a lot less pretty, I think. I think it could be improved a lot. But at least for low numbers of fields, we were able to construct the complete set of primaries, which you would expect, verify that they were primaries, and you get some explicit form. Maybe not organized very nicely. Okay, so now we want to do something like the vector model. So this would have some relevance free vector for holography. In this situation, what changes? Well, because of the case...
come back to are you going to go back to the scalar case? No.
No.
So, may I, let me ask you a question about that. So okay, so now you can in principle count all states?
Yeah.
You have formulas you can put all together and count all states?
Not very explicit. So for the extremal primaries, completely explicit. For the leading twist, completely explicit.
Right.
For the others, much less explicit. I mean, they're formal expressions.
Right, because you can write a path integral, right, for the theory.
Absolutely.
And this has to agree with the path integral. Right?
Yeah. You mean for the counting?
Yeah.
That's guaranteed.
That's guaranteed to work, no, of course, but
No, I mean, the non-trivial thing is decomposing into primaries.
no, of course, but
I mean, he started with the product of characters, which is very helpful.
Yeah.
well, if you get the number of primaries wrong, then it doesn't agree, right? It is true that when you do the path integral, it doesn't come organized in primaries. That's true.
Yeah.
But okay, then you have to get the number of primaries correctly, so it agrees.
Yeah, but starting point was the number of states, which is guaranteed to come from somewhere.
No, I agree.
Okay, so when you go to the vector model, what changes? So in this case, each field picks up a vector index, and you contract these fields in pairs. So the symmetry is no longer that you can swap these two end fields amongst each other. I can swap pairs. I can swap the first pair with any other pair, or I can swap pairs of fields that are being dotted. So what group is that I can swap these n objects and those two things inside there? That's the real product of Sn on S2. And what you need to now do is, you still form the spaces that you were producing before, but you now want to project to the trivial representation of that real product. So this sounds like a really hard problem. For some reason, combinatorists love real products, and they have solved this problem, and they've written books on this problem. So we were able to just lift those results. So we're using the same element over here. This is a formula given for what the analog of chi sim n. This is the analog now for projecting onto the trivial of the real product, and that's what you need to calculate. So you do a little bit of algebra, and that's now the generating function that you obtain. You can again expand this as a power series in T and do whatever counting you like of the fields. We again introduce a z, which has got the denominator removed, and then finally we replace the characters by the power. So that same step again. So after you've got the generating function, everything else is exactly what you did before. So here are just some results. This is what the leading generating function for the leading twist primaries looks like. In this case, what's interesting is it's not freely generated ring. You already get constraints sitting over here. And this constraint comes because the square of that generator is one of those generators times that one. And we were able to verify and make sense of that numerator and this numerator sitting over here.
A capital N is finite in everything you're doing.
Absolutely, yeah.
But in the large N limit, everything should simplify.
Absolutely, yeah. If we trace over projections to the trivial of Sn of S2, in fact, it turns out that these formulas over here, given by an honest counting of the states, agrees completely with this generating function here. What's going on here? You need to sum over all Young diagrams of 2n boxes, and this lambda even, what that means is every single row length in your Young diagram must have an even number of boxes. So previously, for example, if we had 4 fields, The only representation that we would have had here is a single row with 4 boxes. In fact, it turns out that the trivial representation of the Reed product comes once from a representation with 4 boxes in one row, and once from a representation with 2 boxes on the first row and 2 boxes on the second row. So this sum over here, only when you sum over the even Young diagrams does it agree with the counting. And then once again, you can do the construction just by acting with the projector of Sn on S2 on the polynomial, and that again gives you formulas now for the primaries of the vector model and constructed using any number of fields. So now for the matrix model, in fact, now you have a very rich structure because you have 2 indices, and there's a lot more you can do when you form your observables. So one prime you could make would be by sprinkling derivatives onto trace phi squared and trace phi. Now in this situation, what are the symmetries that appear? You've got an S2 which swaps the 2 fields sitting inside that trace, and an S1 which, well, that's in that field. So if we want the trivial, what we need to do is we need to pick up a representation of S2 times S1, which is the trivial of S2 and the trivial of S1. How is this representation obtained? If you restrict this representation of S3, you get that representation once. And if you restrict this representation of S3, you get that representation once. Now, when you come to do the counting using these generating functions, it's a little bit more involved. So, for example, if you multiply that with that, you can get that once. So there's a coefficient of 1 here. If you multiply the hook with the hook, you can get the hook once, and you can get that once. So there's a 2 sitting there. So you have to go on, arrange so this is the external primaries, arrange the z's and the w's in such a way that you keep getting that trivial of S2 times S1, and at the end of the day you get a nice counting function for sprinkling derivatives of that particular combination of fields, and this again matches with the answer that you would get by just doing a straightforward counting using the conformal group. If you sprinkle derivatives instead on trace phi cubed, now the symmetry is Z3 because you can cyclically commute the matrices inside the trace, and that's a symmetry. So you now have to ask, when do you get the trivial of S3? And that's subduced once by the symmetric and once by the antisymmetric. So now you go ahead and you again add up the guys that can give you these possible representations, and you again reproduce the counting that you would have done by sort of more mundane methods. So again, it means that you can take a symmetric group projector, act on some set of polynomials. Once you've got the polynomial, you can translate that back into an operator, and that will be the primary built with that particular trace structure. We've also got formulas where you do some Fourier transform on these, and you get things that are classified by representation of the symmetric group and all of that, but so I will not go into that.
I probably missed it. You always start with some particular trace structure and then sprinkle derivatives?
Yes.
And what about the trace identities?
So in fact, so great question. The reason why we took a Fourier transform was to go to representation space is that there the trace, so in that situation, you would have primaries labeled by a representation of Sn, and you would cut off the number of rows, and that should take into account the trace identities. Right. So that's our thinking. We didn't check that at all.
Right.
Okay. For free fermions, you have a slightly different starting point. And so there's the product that you would compute, and you do exactly the same thing. These are again the numbers that you would like to get. We again remove the denominators. We again turn the chi j just into powers of x and y, and that's again the object that we're interested in. And if you do the counting, that's the leading twist counting. It agrees on what you get from characters. That's the counting for extremal primaries. It agrees on that was from characters, and that agrees with the symmetric group formula. The difference now is, previously we were projecting onto the trivial representation because the bosons are invariant under swapping. Now we project onto the antisymmetric. So we would pair the symmetric with the antisymmetric, symmetric with the antisymmetric, and the product of these two guys has the symmetric in it once. So all those coefficients are right. And the counting matches, the character counting. So again, the fact that the counting matches tells you can realize the polynomials corresponding to these primaries and just some projection operator again acting on the z's and the w's, the hook variables that you form. And you can turn that into an operator. So is there a representation now for the fermions? Yes, there is, and you construct it in the same way. So K is again, going to tell you things of translation invariant. There's the dimension of the fermion, also appearing over there. So P is slightly more involved. Now you have to require that it's a primary, so annihilated by the special conformal generator, and the equation of motion looks slightly different. But again, you can write down polynomials that obey this. Holomorphic translation invariant polynomials are again a very simple class. And so you again very easily reproduce the highest concurrence. In this case, you have to have an odd power because you want it to be antisymmetric under swapping Z1 and Z2. And again matches the answers in the literature. And well, there's two more primaries just as examples that weren't written down. Okay, good. So, future directions. So I think that we've displayed a new algebraic structure. So the primaries of the free field theory close a ring. The product of this ring is not the usual OPE. So the way that this product acts is you fixed n, you fix the number of fields, and the thing that you're taking the product of are the derivatives acting on the fields producing the primary. But that is a ring structure. You've got the usual OPE, which is a different algebraic structure, and you could ask what's the interaction between the product of our ring and the OPE. And well, if you're optimistic like we are, you might hope that we're going to learn something about OPE coefficients, and that's what we're trying to do now from the coherence of those two products. The other thing that I think would be interesting is just for a small number of fields, for both the free matrix and the vector models, write down explicitly some examples of primaries. We'll get some infinite families of primaries. This will be beyond the highest concurrence. For the free matrix, this will be relevant for the tensionless string, for vector models, for some sort of higher spin theory of gravity. So that's something that's very doable. We have so far considered a single Weil fermion. I think that it would be much more interesting to consider free Dirac fermions, and I think it would be straightforward. Maybe a less trivial extension, we could start considering free gauge fields. Another thing to ask is if any of this survives when you add interactions. So one of the things that we're looking at is sit at the Wilson-Fisher fixed point and work to one loop. And can you carry out this analysis, even at one loop? And then finally, these applications to affect the field theory, what people are trying to... so I would have thought this isn't phenomenologically interesting, but it seems lots of phenomenologists do this. But they try to write down what's the space of a complete list of operators that you could add to your Lagrangian. I don't know why something with a dimension of 200 or something would have any physical relevance, but they seem to like making these long lists of these operators. And our methods would definitely be used to answer some of those questions. Thanks for your attention.
So there's time for a few more questions. Antal?
So Shiraz suggested that things simplify in the large anime. This was very nice, but so how do they simplify?
So we haven't looked at that in detail yet, but that is something that would be interesting to pursue.
Maybe Shiraz can.
Yeah, so
Is there a picture that I can see? Some picture.
well, I was thinking of something very nice, which is this. That suppose I take. We know that the operators of two phi's are the high-speed representation, so conserved high-speed currents, right? So 2, 0 plus, and so on. Now, if you want the operators with 4 phi's, it's the product of these representations.
Yeah.
So, something you could try to ask, I don't know the answer, representation theoretically, is can you find the Fock space of this stuff? You know, in the large n limit, the answer should be the Fock space of these representations.
Yeah, there should be a Fock space.
Now, I don't know how to answer that representation theoretically, but you see, what happens at finite n is that the equivalent of trace identities will cut this off.
Yeah.
But at large n, that never happens. So your answer is, there's a second representation theory question that you could ask, which is instead of starting with the free fields and taking their Fock space, you start with this list of representations and take their Fock space. And in large n vector model, these two show.
Any other questions? Yeah.
Maybe you mentioned on this, but there is a symmetric version of all this, like superconformal?
So that's something on the to-do list. So I think that, for example, if you're looking at a free fermion and free boson, I mean, this would generalize immediately. And then you could decompose things into superconformal multiplets. So we haven't looked at that, but that is something that we would.
Are there things you can take from textbooks in that case, or you have to invent? For many of these, there's like symmetrical.
Yeah. No, I think that if you're considering a single field, I mean, we don't need to use things that we've done already. So I think it would just be a case of putting them together correctly.
For this Wilson-Fisher thing, is the only complication that you have to change the equation of motion, or do you have to do something more than that?
Okay, so for the Wilson-Fisher thing, the equation of motion definitely changes. And so the reason why that is so interesting is the original phi field that you had was saturating the unitarity bound.
Right.
As soon as you have this anomalous dimension, it becomes long.
Right.
So you get some sort of version of the higher spin Higgs mechanism.
Right. So now all these higher spin things, they're gone. So
They're gone. And also the higher spin currents, they also pick up a dimension.
Right.
So that's the kind of stuff that we want to probe. So it's not even obvious that you can phrase it in this nice tensor product of vector spaces language, and that it all goes through, and that there's a ring behind all of this, and there's still such a nice description of the primaries.
Okay, if there are no more questions, let's thank Robert again.